All right, we'll continue our discussion on discrete optimization. As we've seen, discrete optimization problems can be very challenging because of the combinatorial nature of them. So we often look for a structure that we can take advantage of. Last time we saw with branch and bound that integer or more generally convex problems, sorry, not integer, linear problems, we could take advantage of that structure where we could guarantee a global optimum and cut off branches and efficiently come to a solution. Dynamic programming is another technique where we can utilize some structure to more efficiently come up with optimal solutions. I should say that dynamic programming, although I introduce it here in the context of discrete, is actually a broader approach. It can be used with continuous problems and even is as well used outside of optimization for just algorithms in general. The main thing that, or say the structure that occurs is what's called a Markov chain. For a continuous version, we would call this a Markov process rather than a Markov chain. And in either case, what it means is that it's the chain or process satisfies the Markov property, which is that a future state can be predicted just from a current state without having to know a full history. So just to give you an example, let's say on your cell phone, you were writing this a tool for the keyboard to predict what word you were going to say next. So let's say you just type the word, I don't know, let's say car, and it might say, well, maybe you're going to say door next, or a car, car garage or something, whatever. There may be various words, and the reason why we would say this has a Markov property is that this is not to say that this is a fully predictive in the sense that you could write, of course, whatever. You could say car garbage or whatever, but we're going to model this as these are the states that you are going to transition to, and we may put probabilities on them. We might say, well, this is a 12% probability here, and there's a 15% probability here. These are called transition probabilities. But the idea is that we only depend on the current state, not a full history. So in other words, I don't really need to know or really care what word you typed a minute ago, 20 words ago, whatever that word was, it doesn't matter to me. I just need to know this word. And this Markov chain can be extended a bit. We can relax this requirement that it's just one state to have a finite number of states, still not a full history, just a finite, and we call this a variable order Markov chain. The nice thing though is that if this property exists, that we can take this complicated problem, which is large, and break it up into this recursive one where we're solving a sequence of smaller problems. And then those smaller problems help us build up towards the larger problem. So, a general problem, discrete problem doesn't fit this structure. Like if I'm doing an airplane design problem and I've got discrete number of blades on my propeller, maybe a discrete number of motors, a discrete material in the wing, there's not some sort of structure where, knowing the state of the propeller number somehow dictates the wing material. It doesn't really happen. These kind of structures are very common in controls problems, at least in engineering, that's a very common application. And often they have to do with time sequences where we make a decision, and that decision then we'll make another decision in time, right? We're making sequences of decisions in time, hence the name dynamic. Although it doesn't necessarily need to be in time, that's just a very common case. And so I mentioned controllers because often we have, a sequence of control decisions. We want to control this robot, through some action choices in time, hence this name dynamic. Let me start with a more basic example before we get to optimization of just to introduce the idea of a Markov chain and recursion in general. And that's just the Fibonacci sequence, which most of us have seen before. And we could define it this way, that we just need a starting condition. And in this case, we actually need two starting conditions here. f0 and f1. And then the general formula is that f at any n is just equal to the sum of the last two entries. So this is a Markov chain because we don't need a full history. If I want to get f20, I don't need to know what f3 is. I just need to know what f19 and f18 are. And of course, you could say, well, f19 and 18 depend on f3 eventually, and they do. But it's through this recursive process where I've broken down a big problem into a small problem. So let me just write that recursively as if this was a programming function. So we could write a function, right? We could call this Fibonacci function. I could give it some number n. So say you could put in, and we'd say it has to be an integer, can't be a negative number here, okay? So then we could say, well, if n is less than or equal to 1, we just return n. So if n is 1 or 0, we just return that number. Otherwise, we're going to return Fibonacci for n minus 1 plus Fibonacci for n minus 2. And that's the end of the function. And if you haven't seen recursion before, that may seem kind of weird. But what recursion basically means is that we define a problem in terms of itself, or in other words, the solution is like a simpler version of itself. And this will work, right? We can write this in code. This works just fine. But we're defining the solution of this function as basically smaller versions of itself. So this then will call this function with a different number and so on, all the way until it gets back to 1 or 0. So let's look at a picture of this. Here's with a small number, and this grows really quickly, but let's look at Fibonacci of 5. 5 just depends on 4 and 3, and 4 depends on 3 and 2, and 3 depends on 2 and 1, and so on. We work our way back until we get to say 1 and 0, and 1 just returns 1, 0 returns 0. Those return back up to that function, and then that function adds those two, returns back up, and so on, and we work our way back until we get to Fibonacci 5. This is very simple. It's elegant in terms of code, very short, simple, but this is inefficient. As you've probably realized by now. One way you could see this, I've just highlighted that I'm calling Fibonacci 2, for example, many times, and this is a small case. If I put Fibonacci 20, I'm going to call some of these same functions a whole bunch of times, and that's a waste, right? Because I'm calling the exact same function with the exact same argument over and over. Well, there are two ways to deal with this. The first is a top-down procedure, and this is called memoization. And it basically just means that we memorize things that we've already computed. So just to use the Fibonacci 2 example, as I was going down, let's say I went down this depth first chain here. Once I computed Fibonacci of 2, I store that number. I just remember, I store this here in an array. And then later, when I see Fibonacci of 2, I don't call the function again. I just immediately return, oh yeah, the value of Fibonacci 2 is 1. And I come back. Similarly for 3, for anything else that I'm going to see, I just store that value. So there's actually only going to be n calculations. All the rest are immediate returns. So instead of this huge exponential growth, I just have n actual function calls each time I see a new function I haven't seen before. The other approach is bottom up rather than top down, and we call this tabulation. Oops. Tabulation. And this approach is how one is normally introduced to the Fibonacci sequence. We just work from the bottom and we go up. So we again said f0 is 0, f1 is 1, and the general formula was n minus 1 and n minus 2. So that just means I add the last two numbers. So this is 0 and 1 is 1, 1 and 1 is 2, 2 and 1 is 3, 3 and 2 is 5, 5 and 3 is 8, and so on. So if I wanted to do Fibonacci 20, I just work my way forward, and there'd be 20 steps. We can also write this as a function, and this is we can do this. We can take these recursive formulas and change them into loops, and that's what we're going to do here. So I can write this alternative function. Actually, I might need slightly more room than that. Here's my new function for Fibonacci. And what I'm going to do is I just initialize those numbers like we did. And then I'm going to create a for loop, right? So for I equals, I already know 0 and 1, so 2 up to n, right? This is just a for loop. And then I say f of I is f of I minus 1 plus f of I minus 2. And of course, when I get to 2, right, I already know 1 and 0. And then the next time to the loop, I have 3, I know 2 and 1. So I'm just building up this loop throughout. And at the end of the loop, I'm just going to return fn. And that's it. Still very simple formula. And this is the more popular approach, more common these approaches is tabulation rather than memoization. But in either case, we've changed a problem that had a complexity of exponential complexity 2 to the n, right? Because each function had kind of 2 options that we had to pursue. So there's 2 to the n options, now to a linear complexity where there's really only n functions that we need to evaluate. Okay, so let's maybe start thinking about a context of an example. We'll put a little more math behind it. So here's an example we've seen before, and I'm actually going to solve this today, not quite yet. But let's start transitioning over to optimization. The Fibonacci sequence is just, it's just a sequence. It's an algorithm, we could say, a formula really, but it's not an optimization problem. The main difference here in the optimization is that we're going to make design decisions. We have decision variables or design variables, and those are going to change the next state. So as a picture, we would normally write like this. We would say I have some state I am at, and based on some decision that I make, it's going to transition me to a new state, right? And then I may make another decision and transition to another state. So I have a sequence of decisions that I make, again, often in time, but not necessarily in time. So as a simple example here, we have this graph, right? This weighted directed graph. And let's say I'm at this state here. There are only 2 decisions I could make here. So my design variable will be like, say, 1 or 2 to depend on which choice I make. And if I choose 1, it transitions me to this state. If I choose 2, it transitions me to this state, for example. Okay, so this is a fairly simple case, but to write it generally, we would say that the state, our future state, is some function of my current state and my design decision. And we call this T here, we call this a transition function. Okay, so again, in the graph, it's not much of a function. It would just be, if xi is 1, the next state is 6. If xi is 2, the next state is 7. It's kind of a boring function, but it could be a complicated one. So for example, let's say we're trying to fly, this model airplane, and the state is, my position, orientation of the airplane. And my design decisions are some control inputs. I'm going to change on my controller the throttle setting, or maybe the elevator setting, and I want to see what my next state is going to be. I may have a dynamic model of the airplane, but it may be somewhat complicated, not just because of the dynamics, but there also may be some stochasticity to it, maybe some randomness, right? Or some uncertainty because say, there's going to be wind, even though I put in the same inputs, because of the environmental conditions, I may get some somewhat different outputs, or because my elevator, isn't super tight, maybe it changes a little bit depending on, some random variability. So this could be in general some complicated function. The other function that we have is a cost, right? So each decision that I make has a cost function associated with it, right? So I'm at some state, I make a decision that has a cost. And this is what I care about. So again, let's say I was at this state and I could choose between these 2 decisions. This one has a cost of 4, this one has a cost of 6. And this is what I'm trying to optimize on, not just the cost of this decision, but the cost of a sequence of decisions. And so this cost function may change at every iteration. Again, in this simple example, the cost is just this number, but it may be, like in the helicopter, let's say, or airplane, I guess I was saying, I wanted to get from these waypoints, fly my airplane from one place to another, or do this maneuver. I wanted to, do an elevation climb, get to a new altitude state. The cost may be that I want to do this with the least amount of energy possible. So for a given control decision, it's going to use some energy, and then I make another decision that's going to use some energy. I want to choose a sequence of design decisions that are going to minimize my overall energy expenditure. Or in this simple example, I want to make a series of design decisions that are going to minimize my overall cost in this path. All right, so let's write that down. What we're actually caring about is not just the one cost, right? It's actually the sum of all these costs. I want to find the minimum. I want to make a decision or a design decision that's the minimum of the cost for this current decision, plus all these future decisions, right? I've got, I'm going to be at a new state. I'm going to make another decision all the way up to, I'm running out of room, so write it below n. Right? We usually, an n defines what we call a finite horizon. If it's a continuous problem, it could be an infinite horizon, but we usually have some fixed number of horizon we're looking at. So in this problem, this is the sum of those costs and our altitude change of airplane. It may be, the sum of the time steps it's going to take to get me to that next altitude. Right? So there's some finite horizon I'm looking at. And I want to make a series of decisions that are going to minimize the total cost across all of them, right? Not just one. It doesn't make sense if like I make a decision that takes very little energy right now, but I'm gonna have to pay for that later. I want to find the lowest energy or lowest cost across all those decisions. And we call this the value function. And to emphasize, the value function is not just what's the sum of the cost for some set of decisions. It is the optimal cost, right? It's the optimal sum of the cost. It has that minimum in front. So it is the best that we could possibly do, considering all the future decisions that I can make. Okay. So this, because of the structure that we have, Bellman, I'll write down Bellman, he came up with what's called Bellman's principle of optimality. And his principle states that because of the structure, this Markov structure that we have, that if, let's just postulate, let's just say for a moment, let's say I knew the best decision to make in the future at time xn, and for the previous time step before that, all the way until the next time step. Let's say I know what the best decision to make is. Somehow you just told me, like, I know all the best future decisions. Then Bellman's principle says that we can determine the best possible solution to solve this problem just for this current time step. So that sounds not that great, but what it means is actually really great. It means that we can do kind of like what we were doing before. We could start at one end. We could start with this problem. Let's just say there was only one time step left, and let's solve that. I can solve that problem now because it says I just have one time step. I can find the very best decision for just that. Now I've locked that in. I know xn star. I go back one, and I can, because this is known what the best possible thing to do is, I can figure out what the best possible thing is to do at this time step, and I can work my way all the way back. And by the time I get to the front, I will have the best decision sequence for the whole thing. Now that sounds kind of like a greedy algorithm, right? That we're kind of making the best and locking it in. But it's not, because of the structure of the problem. We'll see this more clearly in an example in a minute. So let me just finish a little bit of the math here, and then we'll get to that. In an equation form, what this would say is that the value function is the minimum across all the decisions that I could make. So I have to, across all these decisions, right, of the cost of my current decision, plus I'm kind of now deferring the problem. I'm recursively sending it off to the value function at my next state, right? I've kind of simplified it and said, well, I've recursively defined it. Like my value function is now a function of another value function, which is the next one, and so on. So I work it all the way towards the end where it just is now a simple problem, and I can work back and back and back. Okay, just to make it clear that this is coupled. It's not that I'm making a decision. Oops, sorry, I wrote that really sloppy. That's an X. I'm making this decision. It's not independent, right? Like this value function is not independent of the decision. So if I could write that explicitly, remember if we go back that this state depends on the current state and my current decision through this transition function. So we could write that more explicitly like this. We could say cost, right, plus the value function, which depends on the transition function of my current state and my decision. So my decision, of course, is affecting not just, my current choice, but all the future choices, right? Just like here, if I choose to go here, well, that's affected all of my future decisions as well. It's limited some of my options. Same with my airplane. If I choose a specific throttle setting at this time step, that's going to affect where I'm going to be at in the future. So it's not an independent choice. Okay, I know this is a bit perhaps abstract. Let's see how this could work on the graph problem that we were just looking at. So as alluded to, we want to use Bellman's principle, which means we're going to start at the end and we're going to work our way forward. So the idea is kind of like this. Imagine, let me just get a really thick marker here and just color this up. Let's start with a really dumb thing. Let's say this was the whole problem. Well, that's kind of boring. Actually, I'm going to back up a little bit because that's too easy. Let's say this was the whole problem. Right, we're starting at the back. This is all I had. Well, in that case, it's pretty easy to figure out what the optimal solution is, right? I'm just gonna go from here to here. That's the best I could possibly do. Okay, so let's back up a little bit further and let's now consider this problem and so on. And we'll work our way all the way back. So let's start with that. What we're gonna do is we're gonna keep track of what the best we could possibly do is starting from where we're at. So we start, let me just get the first two to get us going. This first one is kind of dumb, but we'll do it anyway. Start at node 12. There's nothing to do. You're already there. So there's no cost to be gained there and there's nowhere to go from there. It's just kind of done. Okay, so let's go back one. Let's say I was at node 9. What is the best I could possibly do from node 9? Well, that's easy because there's only one option. It's 3. That's the best I could do. And I'm going, and that's all I really need to know if I want to get just the optimal function value. But if I want to keep track of the sequence of steps, it helps if I write where I'm going next. So that would take me to 12. So I'm just going to keep track of where I'm going next to node 12. Okay, similarly for 10, the best I could possibly do is 6. I mean, that's the only thing I can do. Okay, so the best I can do is 6, and that takes me to node 12. And 11, the best I can do is 2. That takes me to node 12. Okay, so those aren't super interesting, but let's do a more interesting one now. Let's look at node 5, okay? So here's what Bellman's equation says. The value, meaning the best I can do from 5, is going to be, right, it's this formula here. It's the minimum of my cost plus other value functions. It's going to be, and I got to do it over all decisions. I'm going to write, it's the minimum of, and I've got 3 possible decisions. It's the minimum of, let's say I choose here, 3. That's the cost of choosing this, plus the value of 9. Remember, the value means the best that you could possibly do. So the best of 9. Of course, that one, okay. Sorry, the second one here is 2, right? That's the cost of this one, plus the value of 10, or the best that I could do from 10 onward. Okay, 2 plus the value of 10. Or 1 plus the value of 11. Okay, so if you notice what's happening here is that the whole problem is really kind of hard because there's tons of combinations. But what we're doing here is we're reducing this to a sequence of simple decisions where in each case, I only have to consider a few options because all of these things are now depending on things that I already know. I already know the value of 9. I don't have to go now and figure out, well, what's the best I can do from 9? I know that, it's just 3, right? So this number is 3. The value of 10 is 6. The value of 11 is 2, right? And I'm just grabbing these numbers from here. Okay, so if I look at this, this is 3 plus 3 is 6. Let me just write those. This is 6, this is 8, and this is 3. So the best I can possibly do from node 5 is 3. That's the minimum. Okay, so I'm going to write that this is 3. And that resulted by choosing the next step was to go to 11, right? So that was the best I could do. Okay, so that's the process. And again, the idea here is that I just have to visit each node once, and each node doesn't require kind of this, elongating thing where visiting that node then branches off to a whole bunch of places. Each node that I go to just has a few options, and each option just involves these simple lookups of things that I already know, numbers that I already know. So there's not much computation. All the computation is really just taking a minimum of a few numbers. So this can be done efficiently. So I won't continue that, but if you want to see it worked out more fully, first I would try it yourself, but then it is worked out in the book, but this is what it looks like. We actually saw this before. And this is actually, we know, to be the global optimum because of that structure. And we could do this, even though this example is small enough, we could figure that out. We could use the same kind of process with a bigger example, and it will work well, again, because of the structure. Okay, in this last segment, I want to talk about another example of a problem that a common one in discrete optimization, or a well-known one. It's called the knapsack problem. Another famous problem, kind of like the traveling salesman problem, is a famous discrete problem. The idea in this problem is, let's say you have this knapsack. So I've got this bag here, right, that fits stuff in it. And I have these items. There's these items in this room, and each item has a weight associated with it and a cost. Okay, and each item has a potentially different weight and a different cost. And the problem is that my knapsack has some capacity K. I can't fit in an unlimited amount of stuff. I can't carry everything out of here. Okay, so there's a bunch of stuff in the room. You know, maybe my house is on fire and I'm trying to grab a bunch of things. And I'm trying to decide, what should I take to maximize my value here, maximize the cost. So let's say we would maximize, actually, let me write the variables first. Make it maybe easier to understand. My design variables are going to be these discrete numbers, either 0 or 1. So it's a discrete problem. It's called 0 to 1 knapsack problem. And that means that 0 means I take item I, or sorry, 0 means I don't take item I, and 1 means I do take it. So I have n design variables, 1 for each item, and I'm just trying to decide, should I take this item or should I not take it, right? Which one should I take? And so I want to maximize the sum of the cost times x, right? Because each x is 0 or 1, so if I take it, it's a 1, and so then I get that cost. I say cost, normally we would say like maximize value or minimize cost, but just to be consistent with our previous nomenclature, we're going to use value to mean the optimal. So I'm going to continue to use cost here. Hope that's not too confusing. And then I have the constraint that the weight, and right, this will only select the items I actually take, right? Because if I don't take it to 0, I need the sum of the total weight to be less than my capacity that I can carry. Okay, so this is the knapsack problem. Sounds maybe somewhat contrived, but it's a very practical problem. It's used a lot in resource allocation. We do this every day. When I say we, I mean just, you know, human nature, that we have to make decisions because we have fixed resources. I have fixed amount of time in a day, for example, and I have to decide amongst the many competing activities that I could participate in a given day, how am I going to spend my time? So that's my fixed knapsack. My time, different items are going to, or different activities or things that I do are going to take different amounts of time, and they're going to give me a certain amount of utility, and I'm maybe trying to maximize my utility for a given time constraint. Okay, so this is a very common life problem, but again, also lots of resource allocation problems, especially things that involve time and budgets, right? That we need to stay under some fixed budget or time and figure out how to, you know, either choose items or allocate resources well. So this can be posed as a Markov chain. And the way we're going to do that, again, the whole idea is that we take this hard problem where I want to find what's the optimal set I should take. And again, if the numbers are small, it's easy. But if I've got lots of options, this is really hard, is that I want to break it up into a small problem. So the small problem I'm going to say is, let me try to find the value, meaning again, the best I can do. If I have some capacity K, and notice K is a lowercase k, meaning it can be a number that's less than big K. So I'm going to allow myself to reduce a smaller capacity, and I consider fewer items. I. So this is a capacity. So I'm going to allow my knapsack to change in capacity so I can solve a smaller problem perhaps. And I'm going to consider fewer items. I'm going to consider items 0 through I. That doesn't mean I'm going to take all the items 0 through I. It means I'm only going to consider them. So let's say, for example, I'm going to try to solve the problem where I only think about there's only one item. Or then I'll next try and say, well, what if there's just these 2 items? Okay, and then I'll say, what if there's these 3 items? So I can build up in complexity because of this, again, this Markov structure. All right, so again, there's kind of structure that I can solve. As we'll see, I can solve this problem. Let's become clear maybe next by solving smaller problems. And the real problem that we're interested in eventually, right, is that I want to know what the value is if I use big K, all my capacity, and I consider all the items. But I'm going to build it up to it using tabulation. Okay, so kind of in the interest of time, I'm not going to work this out in great detail, but I want to introduce kind of the main heart of the idea here is that I have this simpler problem, and I'm going to just think about that. So again, what this means is I've got a smaller capacity K, and I'm only considering a few items I. Now, the thing that we're going to assume now is that I've already solved the problem with one fewer item, right? Because we said we could do this maybe recursively. So maybe I'll think about the case with one item, and then two items, and then three items. So let's say I've already solved it for I minus 1 items, and I'll also add for any K, right? So I solved it for no matter what capacity, I've solved it for 3 items. And now I want to consider what if there's 4 items? And once I do that, and I solve it for all the capacities, I can now think about 5 items, right? So this is how I can break up this harder problem into a sequence of easier problems that can be done recursively or now in a loop, so I don't have to try all these tons of possibilities. I can reuse optimal solutions. Again, remember, V is an optimum, the best I could do. I'm using Bellman's principle. Okay, so all I care about now is this sub-problem, and there are actually only a few options. So let me just draw again, like here's a bunch of these items, and I've already considered all of these. I don't need to consider them. I'm now just considering one more item. It has a weight, has a cost. That's the only item I'm considering. And there's only a few things that could happen here. One thing that could happen is that it's too heavy, right? So if the item is bigger than the capacity that I have, I can't take it, right? So what's my value function? Now the value function at I then is going to be just exactly equal to the value for that capacity at I minus 1, because, you know, I already figured out what the best I could possibly do with these items. So if I add this one more, if it doesn't fit, well, my value is unchanged. If that's not the case, now the weight could possibly fit in this capacity. I have two options. Either I take it or I don't take it. Right? So let's say here's else. Say I don't take it. What happens if I don't take it? Well, that's the easier case. My value is unchanged, right? In that case, my value would be unchanged. Because if I don't take it, you know, I still get the same value. But let's say I do take it. What's my value here? This one's a little harder. The value is going to be the capacity, the best I could possibly do with the capacity that is reduced now by the weight of that item and with one fewer item. So let's say that again. So let's say I take it. Oh, sorry, I missed something there. The best I can do if I take it is I get the cost. So I just chose this item. So I get the value, I get that cost, and it's the best I could do with the remaining items, which are I minus 1 items, right? And with a lower capacity, right? Because I took this item C, so I've reduced my capacity by W, so I need to consider what's the best I could do. Remember, that's what V means, the best I could do with that reduced capacity and one fewer item, okay? So this is almost done with the algorithm. So what we're gonna do now is, again, kind of like our simple example, because we solved already all the I minus 1s, these are things that are known. I know this is just a number. And I know this is just a number. We solved it, right, for any capacity. So this is just a number. This is just a number. I know my cost. So these, I just compare two numbers, and I'm just going to then take whichever one of these is bigger. So I decide, do I take it? Do I not take it? And so the way this is going to work, and again, I'm not going to do this in detail. There's an example. I have to do this in a double for loop where I start at the very beginning with 0 items. This is my initial condition. With 0 items, my value is 0, no matter what the capacity is, right? I can't get any value if I don't consider any items. So that gives me my initial condition. Those are my I minus 1s. I now move to I. I is going to be 1 now. I'm going to consider each one. And I'm going to start with a capacity of 0. I'm going to work up to 1, 2, 3, all the way up to my big capacity K, solving each one of those. And then I have now solved all the cases where I have 1 item. I consider the 2 items and so on. And I can work my way up. So this does take a double for loop. So the complexity of this is, let me just write a little sidebar here. I got a room. The complexity is K times N, right? That's better, especially as N gets bigger usually, than 2 to the N, which is what the complexity is in general, where I'd have to consider all the possible combinations of each N item, right? Do I take it? Do I not take it? There's 2 possibilities. So with N items, there's 2 to the N. So this grows exponentially. This doesn't grow as fast. We'd say it's pseudo-linear for a given capacity. So as long as the capacity isn't huge, it becomes harder as K becomes bigger and bigger. If the capacity isn't huge, I can consider quite a few items generally. And again, because of the structure, where this is not a greedy problem, this is actually using the fact that we know, kind of like we saw with this case, that each time we know, we're building up the best I could possibly do. And I'm using, okay, take this step and the best I could do from there. And then from here, I'm saying this decision plus the best I can do from here. Same kind of idea with this knapsack as they were thinking, okay, what's the best I can do with 1? Now with 2, I'm going to say, should I take it? What is the cost of taking it plus the best I could do if I had taken it, or the best I could do if I hadn't taken it? And now, because I know that they're the best possible, I can compare them and get the actual optimum. Again, this is Bellman's principle of optimality. So encourage you to look in the book if you want to see that worked out in a little more detail, or maybe practice it on your own. So to recap here, you may have got kind of this sense, but I just want to make it explicit. Dynamic programming isn't really an algorithm like some of the others, right? Like DFGS or genetic algorithm or whatever. We can write an algorithm. We can't do that for dynamic programming because it's really more of a technique. In that sense, it's more like greedy methods, right? Where it's more of a concept, an idea, where we take a Markov structure, if we have Markov structure, a Markov property, that we can use that structure to our advantage, write the problem in kind of this recursive sense where it's now a reduced problem. And that we can do, you know, typically with this tabulation method where we do kind of a loop and build it up. So the complexity doesn't become exponential. It's often linear, pseudo-linear, things like that. So much reduced costs. The specific algorithms, right, will vary kind of by the problem. Like, so for the knapsack problem, we can write an algorithm, but for that weighted graph, the algorithm's a little bit different. Again, it's more the idea. If you look in controls, which again, I say is a popular or a common application of dynamic programming, you'll see various specialized methods. And so there are many out there, but this is our introduction to dynamic programming. Next time, we're going to talk about simulated annealing, and that'll be our last topic under discrete optimization. See you then.